When we talk about quantum computing, we usually get caught up in the brilliant algorithms and the super powerful processors. But what about the tools, the actual instruments that make it all possible? The ones so precise they can measure a world a million times smaller than a grain of sand? Welcome to our Quantum Deep Dive. Today, we're telling the story of a hidden giant of modern technology. Now, he didn't build the quantum computer itself, but let me tell you, without his invention, we'd have no way to even read what's going on inside one. Exactly. And for this explainer, we're diving into a fantastic essay by Jörg Oe Schneebat. He's the one who pieced together the incredible journey of this pioneer, and it all starts with one fundamental, almost impossible problem. Right. How do you measure the quantum world? We're talking about a realm of impossibly small signals, where the simple act of looking can literally change the outcome. What you need is a measuring tape of almost unimaginable precision. And for decades, that was the huge hurdle. We could dream up theories about quantum mechanics, sure, but building the tools to actually interact with it, to measure it reliably, well, that was a monumental challenge. It's one thing to have a map of a new world. It's another thing entirely to build the ships to get there. And the person who built one of the most important ships for this journey was a physicist named John Clarke. He basically dedicated his entire life to solving this exact measurement problem. And in doing so, he laid the groundwork for a technological revolution he probably never saw coming. Clarke's journey kicks off in post-war England. He was fascinated by magnetism, which led him to study at Cambridge and then to do research at the legendary Cavendish Laboratory. And this is key. It was there he worked alongside Brian Josephson, a collaboration that turned out to be absolutely central to his own breakthroughs. Then, by the 1970s, he took all that expertise over to UC Berkeley and established a lab that would become a world leader. And through this whole journey, there was one thing that just drove him, this one obsession, a very strange and incredibly powerful phenomenon called superconductivity. And it was this obsession that would lead him to his greatest invention. Yeah, that obsession with superconductivity led him to create what you could call the world's most sensitive compass, a device that can measure magnetic fields with a precision that was, frankly, just unheard of at the time. Okay, so to really get what he built, we need to quickly grasp two key quantum effects. First up is superconductivity itself. At ridiculously low temperatures, certain materials lose all of their electrical resistance. Electrons just flow through them perfectly, with absolutely zero energy loss. You can think of it like the ultimate electrical superhighway, totally friction-free. The second piece of this puzzle is called the Josephson effect. It was actually predicted by Clarke's colleague, Brian Josephson. It describes this bizarre quantum behavior where pairs of superconducting electrons can tunnel right through a thin insulating barrier. You get a current, but with no voltage. This junction acts like a tiny, highly sensitive quantum gate. And this is where Clarke's genius really shines. He didn't discover these effects, but he had the brilliant insight to combine them. He realized that if you put these two principles together, you could create something truly extraordinary, the superconducting quantum interference device, or as it's known, the SQUID. So, how in the world does this thing work? Well, it's actually beautiful in its design. First, you make a tiny loop out of a superconducting material. Then you stick two of those Josephson gates into the loop. Now, when even the smallest, most minuscule external magnetic field passes through that loop, the current flowing through those gates changes in a very specific, predictable way. This lets the SQUID translate a nearly undetectable change in a magnetic field into a voltage we can easily measure. It's ingenious. And here's the real quantum magic at the heart of it all. The magnetic field that can pass through that loop is quantized. What that means is, it can't just be any old value. It can only exist in specific, discrete, little packets of energy. A great way to think about it is climbing a ladder instead of walking up a smooth ramp. Each rung on that ladder is a tiny, precise amount of magnetic field, and the SQUID is so sensitive, it can detect a change of just a single rung. And that quantization is exactly what gives the SQUID its superpower. I mean, how sensitive are we talking? It can reliably measure a magnetic field down to the picotesla range. That is 1/1,000,000th of a Tesla. To put that in perspective, that is 1/1,000,000th the strength of the Earth's magnetic field. It's so sensitive, it can detect the tiny magnetic field generated by your own brainwaves. It's just incredible. And this incredible sensitivity wasn't just some cool trick for the lab. It opened up entirely new windows into our world. It allowed us to see things that were completely invisible before. from deep inside the Earth all the way to the inner workings of the human mind.
Oh, absolutely. Just think about brain imaging. Before SQUIDs, we had things like EEG, which could tell us when something happened in the brain, but the picture of where it happened was really blurry. SQUIDs made a whole new technology possible called magnetoencephalography, or MEG. It directly measures those tiny magnetic fields from firing neurons, giving us a much, much clearer picture.
What it boils down to is this. For the very first time, SQUIDs gave us a non-invasive, high-definition movie of the brain in action. This tool gave us incredible detail in both space and time, and it totally revolutionized neuroscience and our ability to diagnose conditions like epilepsy.
But the story doesn't stop in the 1970s. Not even close. Decades later, Clarke's invention would become the essential key to unlocking the most cutting-edge technology of our time, the quantum computer.
You see, the challenge of actually reading the state of a qubit is immense. The signal you're looking for is incredibly weak. Meanwhile, the noise from the environment trying to drown it out is incredibly high. And on top of all that, you have to do the measurement with blinding speed before that fragile quantum state just collapses into nothing. Right. So for a superconducting qubit, that's the type that companies like Google and IBM use, reading its state means you have to detect its tiny, fleeting magnetic field. But here's the real trick. You have to do it without disturbing the qubit and destroying the very information you're trying to read. And what was the solution? It was John Clarke's technology. The same principles behind the SQUID were refined to create what are called quantum-limited amplifiers. These are devices so sensitive, they operate at the absolute physical limits of measurement. They can amplify a qubit's tiny signal without adding any extra noise. They are, quite literally, the backbone of readout in today's most advanced quantum computers. Clarke himself actually reflected on this amazing turn of events. He said something like, "When we calibrated the first SQUIDs back in the 1970s, we never dreamed they would one day become a fundamental building block of information processing." It just perfectly captures how fundamental, curiosity-driven research can lead to world-changing applications that no one could have possibly predicted. Which brings us to his legacy. You see, John Clarke didn't just invent a device. He provided the foundational measurement tools that an entire new era of technology is now being built on. His impact is just massive, spanning so many fields. In physics, he proved a core theory of superconductivity. In measurement, his SQUIDs let us see signals that were totally invisible before. In medicine, he made the revolution in brain imaging possible. And of course, in quantum computing, he gave us the essential tool for actually reading qubits. His work is just the perfect example of bridging pure theory with world-changing tech.
Yeah, he didn't just pioneer the SQUID systems and push measurement to its absolute quantum limit. He was also a dedicated mentor at UC Berkeley. He shaped a whole generation of scientists who are now the ones leading the quantum revolution today.
And all of this work was guided by a really clear philosophy. Clarke believed that true innovation doesn't just come from curiosity, and it doesn't just come from a desire to build something practical. It happens at the intersection, where pure scientific curiosity meets a sense of responsibility to use that knowledge for the good of society. So we'll leave you with this thought. John Clarke created the tools to measure what his generation thought was impossible, and in doing so, he opened up entire new fields of science. So it really makes you wonder, what tools are being invented in labs right now that will allow us to measure the impossible of tomorrow? This whole deep dive was made possible by the incredibly comprehensive essay on John Clarke by Jörg Owe Schneppewat. He's the one who did the amazing work of compiling all this history. For more of these fascinating stories about the pioneers of quantum technology, we highly, highly recommend visiting his website at schneppet.de. That's SCHNEPPAT.de. Thanks so much for joining our quantum deep dive, and we'll see you next time.
Schneppet.de is a private project by Jörg Owe Schneppet dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.